Hi guys, it's Professor Stevens. I'm going to go over another example with you here, and I'm also going to do a quick re-overview, that is, from the previous example. In the previous example, I used the textbook to set up an introduction of different ways that we can solve exponential and logarithmic equations, and there were three main ways of doing it, and I'm just going to summarize that here. So the first thing I want to mention is, as I said before, there are three ways to solve these, and the choice of the method will depend on the form of the question. And it can be narrowed down to these three categories: inversion, conversion, so those are the three main ways that you could approach a problem. Now, by inversion, I mean inverse operations. So to give you an idea of what I mean by that, if we had a problem that was linear and we were asked to solve something like 2x minus 3 equals 4, what would we do? We would do inverse operations until x was isolated, right? So instead of subtracting 3, we would add 3 and treat both sides exactly the same way. And then we would have 2x equals 7, and then we would invert the multiplication of 2 to get our answer. So that's what I mean by inversion. And I also want to remind you that logarithms and exponential equations are inversely related. So that's why if you have something like 3 to the x equals 9 to the, 9 squared, if you take the log base 3 of both sides, what that does is it gets your exponent out of the x. I meant to say it gets your x out of the exponent, because we can't solve while it's stuck up there. So inverting the exponentiation, I guess you could call it, inverting that is taking the log of it, same base. And then using the properties of logarithms, we can rewrite this expression with the x out in front. So it's x times the log base 3 of 3. And then that log base 3 of 3 is equal to 1. That's another property of logarithms. And it makes sense because if you have 3 to some power equals 3, you know that power must be 1. And remember, logarithms, they are exponents, they're powers. Right, so that's what I mean by inversion. So some problems lend themselves to inversion, and some problems will be better with conversion. So let's say I have something like 2 to the x plus 1 equals 3. Then I could rewrite this in logarithmic form. I could say log base 2 of 3 is equal to x plus 1. So I've just basically found the inverse of that original equation, and then because this is a value, a real number, I can isolate x now by subtracting 1 from each side, and that'll be my final answer in exact form. So that's what I mean by conversion, so converting from exponential form to logarithmic. So you can convert back and forth. So we've worked on that in a previous section, working on how to change from one form to another. So that's the second way. The third way is matching, and that was what most of the problems in 4.2 were all about, or the method that was the easiest. We used it a lot. So we had something like 3 to the x equals 9, and then we would try to rewrite 9 as a base 3. And then since the bases are the same, the exponents must be the same. right? That's what I mean by matching. So likewise, also, you could have something like the log base 3 of x is equal to the log base 3 of 9. So because the bases and the log bases are the same, their arguments must be the same. So that's actually one of the properties that we start using in this section. And so matching, inversion, conversion, one of those three ways is going to work for any given problem. And it may be that one problem or one way is more efficient than another, or it may be that only one approach is going to really work. So let's go and look at some examples. I'm going to start a new video where I start heading through some, demonstrating lots of different types of problems. And then I will, as I'm doing that, I will point out which method it is that I've chosen to use and possibly why I didn't use another method or why another method wouldn't have been the right choice. See you then.